refiere a algunas infraestructuras mineras en todo lo que refiere a estructuras de relaves. ¿Ya? Así que hoy día vamos a tener en particular esta presentación sobre suelos parcialmente saturados en el contexto de CPT y cómo esto influye en la estabilidad también y el comportamiento de las arenas de relave. ¿Ya? Ahora me voy a cambiar al inglés para presentar al profesor Russell, ¿ya? También a la comunidad que nos acompaña vía online, ¿ya? Que justamente tenemos con colegas hoy día desde Chile y de otras partes de Sudamérica, sino que también tenemos colegas desde países también de habla inglesa. Hello everyone, thank you very much for being here. It's a pleasure to host today Professor Adrian Russell from the University of New South Wales. Professor Adrian Russell has a lot of experience in research and practice regarding the stability of tailings, the behavior of sands, and focusing a lot on the behavior of unsaturated soils with applications to tailings. Today we're going to have a presentation on the CPT, on unsaturated soils, and also on the stability of this type of infrastructure that is very critical for the mining industry. All right, so thank you very much, Adrian, for being here. We are very glad to have you. We are very lucky to have you here because we know that you are heading to Brazil.
Yes.
And it was very nice of you to stop by here in Chile to say hello to us. So thank you very much, and the stage is all yours.
Thank you very much. And this is my first time in Chile and Santiago. I'm enjoying it very much. It is one flight from Sydney to Santiago, 14 hours. So this is very simple for an Australian to come. So I had to take advantage of that and stop for a few days and visit the University of Chile and Felipe. So today I'm going to talk about some research I've been doing on tailings, especially the influence of partial saturation and how that affects strength, stability, and CPT interpretations. So the work has arisen from maybe 5 or 6 years of research, funded partly by the Australian Research Council and some mining partners as well. And there are multiple universities involved, and I'm very grateful to the funding provided by those organisations. The first part of the presentation will talk generally about the mechanics of unsaturated soils and tailings, and then I'll get into the application side of it relevant to the CPT, strength, stability, and liquefaction. So I'll make this a full screen. So my university, the University of New South Wales, is in Sydney. We have around 63,000 students. This is typical of a big university in Australia, 25% international, and it started as an engineering university, so civil engineering is one of the foundation schools of that university. It's very near the beach in Sydney, so it's a very nice place to visit, and you're all very welcome. We are very proud of our rankings. Globally, we are consistently first in Australia for civil engineering, and usually in the top 20 in that discipline, according to the various rankings as well. In the world, that is. The university is quite young. It's 73 years old, but our school is quite big. We have 1,600 undergraduate students, 800 master's students by coursework, and around 200 PhD students. And in the geotechnical engineering group, we have around 6 tenured academics, and some others as well. And we focus on these research areas, but the ones we're most famous for are unsaturated soil mechanics. That's the number 1. And also number 5, our numerical analytical modelling expertise is also very highly regarded internationally, and we also work in these other areas as well. So in the geotechnical engineering group, we have around 25 PhD students from 10 countries, including to South America, and more are always welcome. So please reach out to us if you would like to come and visit. So our PhD program is normally 3.5 or 4 years, but students need to have an honours 2-1 or a first class honours degree to come in. But we also have a Masters by Research program, which is much shorter, only 2 years, but we can also do a partnership type research with other universities. So you're always welcome. It's a nice part of the world. So let's get on to the technical side of the talk. I'll talk about what unsaturated soils and tailings are, and I'll highlight why research on this is very important in the context of tailings. And then they'll go through some of the methods we use, the effective stress, strength, suction hardening, water retention, and what you can do in practice to apply these concepts very easily. So an unsaturated soil or tailings is one where you have solid particles plus air and water in the pore space. They are widely dealt with and encountered in many civil engineering applications, slopes, dams, compacted soils, but also in the mining sector, ores, tailings deposits, dry stacks are always or usually unsaturated. The behaviour is influenced by suction as well as the presence of air in the pore space. Those two things do different things to the way the tailings behaves. Suction, for example, is a capillary action and it pulls particles towards each other, increasing contact forces. It increases the effective stress and it increases the strength. The presence of air also has a significant but quite a separate influence. It means that the tailings is compressible during a fast deformation event. Air is very compressible, much more so than water. So when you have some inside the pore space and you push a cone through it, you cannot assume a constant volume condition. And this applies during cone penetration testing or any fast deformation events like an earthquake or leading up to a liquefaction. You get volume change, and that's very important. We can put suction into an effective stress and then use traditional concepts of soil mechanics to an extent. So we define our effective stress using this equation. It's the total stress plus suction S multiplied by chi, and this is a geometrical correction factor. And then we can put that effective stress into the usual more Coulomb type equation to get a strength and go and do some designs. Suction is caused by a difference between the pore air pressure and the pore water pressure. The air pressure is always larger than the water pressure, and they come into equilibrium through a curvature of the air-water interface. And the difference between the two is what we call suction. Air pressure is usually atmospheric pressure, so the water pressure is negative. It's in tension, and it literally, through this interaction, pulls the particles towards each other, increasing contact forces. There are many obvious examples where you can have a negative water pressure through this capillary action, and this is something you can see in the laboratory. If you have a large diameter glass cylinder where the water pressure is just hydrostatic, so from that red line and below, the water pressure increases with depth. But in the small diameter tubes, the curvature of the water surface pulls the water upwards and holds it in tension in this region here. And then once you reach this level of the large diameter tube, the water pressure is zero, and then it becomes positive below that line. And the same thing happens inside a soil or a tailings. There are places where the water is in tension through this capillary effect. So partial saturation is very important inside tailing storages. Tailings we like to dry out as much as possible, sunshine, and that increases the effective stress and the strength. But then if you deposit more tailings on top and build your structure up and up so it goes higher, you can have these varied sections where the tailings is partially saturated. Okay. And when you do your cone penetration through the structure, you can be pushing through these unsaturated sections. And obviously above a phreatic line as well, you can expect to have partial saturation in significant sections of that. To give you an idea of scale, in a 30-metre high tailings poundment, you can have a phreatic surface that might be 10 metres below ground surface. So you can have maybe 5 or 10 metres above that where it's partially saturated. And even below that line, there can be another 10 or 15 metres of different localised areas where you have partial saturation. And these sections near the embankments especially are critical to stability, so they need to be characterised and dealt with in stability analysis to get an accurate answer. Buttressing is becoming a common problem or a common solution in the mining sector to minimise the risk of failure of these structures. But I'm wondering if the engineers who are designing these buttresses have properly accounted for the suction inside the tailings dam, because what it does is elevate the strength and increases the factor of safety. And I know in many cases they haven't done this fully, so they're perhaps designing a buttress that is bigger than what it needs to be, or perhaps unnecessary entirely. So it's important to put that unsaturated soil mechanics into the analysis to get a cost-effective and accurate solution. So here's an expanded form of the effective stress. Suction is the difference between pore air and pore water pressure. There's that chi parameter. But we also have an air pressure part over here on the left. So we have a total stress minus the pore air pressure, and we call that a net stress. Normally the pore air pressure is atmosphere, and we take that as our datum, so it is 0. But sometimes that air pressure increases and we have to account for that. So you need to be aware of this full expression. For dry conditions, the suction disappears and you just have the usual equation where your effective stress is equal to the total stress. For a saturated condition, chi is 1. There's no air present, and your effective stress equation becomes identical to what we use routinely in undergraduate engineering. And then for unsaturated conditions, you have this net stress plus chi-s is our effective stress definition. Sometimes chi is approximated to be the degree of saturation. That is reasonable sometimes. In other times, it's a very bad approximation. So just be very careful of doing that. And also, there's an alternate set of terminologies and theories based on a 2 stress variables approach pushed by Del Fredland many decades ago. But the ideas I'm talking about here are perfectly compatible with that approach. The chi term is simply the tan phi b over the tan phi in that alternate approach. Now, here's some typical stress strain responses of a decomposed granite when it's saturated and unsaturated. And this highlights what suction does. The first lines I want to show are these. Let me put a pointer. Which is the pointer? This one here. There we go. These are for saturated, loose samples. So you get the classic smooth increase in stress with strain. No surprises there. And you get here volumetric compression as you shear the sample. The void ratio of those tests was around 0.4. Now, these other 2 samples are for when the void ratio is a little bit higher, around 0.47, but they are now unsaturated. They have a suction of 50 kilopascals. Look what happens. You get now a very different response. You get a peak strength and then some softening. and it's looking much like a dense material, even though it's looser than those saturated tests that we talked about to begin with. And that is due to a phenomenon called suction hardening. Suction doesn't just increase the effective stress, it also hardens the soil fabric through a shift of the normal consolidation line or the critical state line. So it does two things to the mechanics. And that is obviously temporary and depends on the suction. So when you wet the soil, that suction hardening disappears. You suddenly reduce the strength. You get volumetric collapse. You change a material that looks as though it's quite dense and strong to one that is very soft and loose and weak. This is the suction hardening phenomenon here. This is the saturated normal compression response, for example, initially quite stiff and over-consolidated, and then you move on to your normal consolidation line. When it's unsaturated, same sort of thing happens, initial stiff response, but the normal consolidation line is now over here to the right. It has moved due to suction hardening. Hardening controls the size of the yield surface. So your yield surface now has become larger through this phenomenon and the shift of the normal consolidation line. And we see the same with our critical state lines. They also move due to the presence of suction by the same amount as your normal consolidation lines. So you need to put this into a mechanical framework to deal with it. These are some real critical state lines for two tailings on the left-hand side there. The saturated critical state line is through here. But when suction is present, and this is a suction ratio of 50, the line shifts quite far upwards and becomes steeper. And then as suction increases further again, it moves. And so you get this suction-dependent location of the critical state line. And another example is just shown below there. So this takes sophisticated and specialist laboratory testing to characterize, and we're very mindful that that is not routinely done in practice. So we try and give advice and guidance that doesn't require this to be incorporated into the mechanics, but sometimes it's unavoidable. These are just some strengths in excess of critical state against state parameter. And you can see that the saturated and unsaturated responses are more or less following the same trends.
The Binan-Jeffries state parameter.
Yes, this is the Bean-Jeffries state parameter. So but the critical state line used in its definition is the shifted critical state line. So again, it's difficult for a practitioner to quantify the state parameter of an unsaturated material. Now, determining Chi-S, which controls effective stress and strength, is important in stability problems. It requires knowledge of what we call the water retention curve or the soil water characteristic curve. This is a signature of any soil or tailings and is one of the first things that we try and measure in a laboratory. It tells us a lot about the mechanics of the material. Generally, when you have a saturated material, degree of saturation of 1, as we increase suction, it stays saturated more or less until you reach a critical suction value called the air entry value. And that is the suction value that is large enough to break the capillary bonds or the capillary forces that exist between the soil particles and enables air to enter the system. And then it rapidly desaturates as you increase suction more and more. But if we get to some point here and then wet the material, so reduce suction, it moves along what we call a scanning curve and then intercepts the main wetting curve and then rapidly moves up to a nearly saturated condition. So we have a main wetting curve down here, a main drying curve, which is out here on the right side, bounding all the data, and then a whole lot of scanning curves that zigzag back and forth between the two as you transition from wetting and drying and through normal seasonal moisture variations or some one or two prolonged wetting or drying events. But the beautiful thing about tailings and many soils for that matter is when you take a double log of the degree of saturation versus suction, you see straight lines form. And that simplifies the mathematical expressions for these water retention curves. And that's what I've been using through all this research. So the dotted lines are the water retention curve. Stays saturated up until you reach a certain suction, and then it desaturates and moves down a main drying curve. The main wetting curve is over here, and then you've got an infinite number of scanning curves back and forth. The slope of the drying curves is alpha. The slope of the scanning curves is beta. And the intercepts with the degree of saturation of 1 are critical parameters. The drying curve intercepts at what we call the air entry suction, and the wetting curve intercepts at the air expulsion suction. I've also drawn on here, using continuous lines, the relationship for chi in terms of suction. Again, it forms straight lines in the double log plane, and that is very convenient. It lets us easily relate water retention to chi, to effective stress and strength using simple power law expressions and straight lines. So the slopes of the drying and wetting curve for the chi relationship are omega, and the scanning curves are here too. Now, mathematically, they look like this, just simple power laws for your degree of saturation and chi, and some typical numbers for the different slopes are given here in this table. Now, one thing we've discovered for many tailings and soils is that this air entry suction scales with void ratio E in a unique way, and the power exponent is 1 minus ds. ds is a parameter called the fractal dimension of the particle size distribution. C1 is just a constant with units of stress and depends on particle geometry and other things. But this relationship between void ratio, air entry suction, and fractals is being derived theoretically, and I'll go through some of the reasoning in a second. We have a second similar relationship for the air expulsion suction. It's just got another multiplier C2 in there. But what these expressions let us do now is do some mathematical manipulations and show that chi-s, for example, can now easily be determined using knowledge of the gravimetric water content and void ratio. And all these exponents are now just slopes of these different curves in this plane. The multiplier C depends whether you're on the main drying curve, so you're undergoing a drying event, or the main wetting curve, if the material's been wetted, or sometimes if you're halfway between. For example, if you're exactly halfway between the two, this is what that constant would be. What is a fractal? Well, it's a special pattern to the grain size distribution that is formed naturally by decomposition of rock, or it is formed artificially by crushing and grinding processes. And sometimes nature just has crushing and grinding involved anyway. So you have this sort of procedure that results in a particle size distribution where you have a very well-graded material and the particles can become perfectly packed. You can have the big grains, and then in between them, the next biggest grains are inserted into the void spaces. And then in the spaces that remain, you insert the next possible biggest grains and repeat all the way down, and you end up with this fractal distribution of grain sizes. How do you know if you've got a fractal in your soil or tailings? Well, you take the double log plot of percentage passing and grain size, And if you see a linear segment, at least for about 2 log scales, then you've got something that's a fractal or very close to it. And the slope of that line in the double log plot, you can easily determine. And then 3 minus that slope gives you your fractal dimension. If you've got a fractal particle size distribution, you'll also have a fractal pore size distribution. And that enables us to do simple mathematics, connecting pore properties to particle properties, because pores and particles share a surface area. So we can do some mathematics and connect them together using that sharing of surface area and relate what is a pore scale property to grain size information. And I just learnt today that Santiago gravel is a beautiful soil that you have to deal with here all the time. And it happens to be a perfect example of a fractal soil. I did this just 1 hour ago. I plotted your percentage passing against particle size for your Santiago gravel. And notice in the double log plane, you get almost a beautiful, perfect straight line. The slope is 0.44. So the fractal dimension of your Santiago gravel is around 2.56. Okay. So it looks something like this image in the bottom left. And I'll come back to that at the end of the presentation with some other estimations. I'm guessing this material is from the mountains, but it's alluvial. But what turns the rock into soil in the first place? Maybe there's some grinding processes through, I don't know, glacial action or landslides coming down or something. And that process, that grinding and churning up of the soil, has caused it to be perfectly fractal, and then the water has just deposited it. Yeah. They compact very, very easily. They're very easy to work with. Decomposed granites all over the world are fractal as well. Anyway, here's the 2 tailings that we've looked at, and I've just plotted water retention curves for them. These 2 tailings happen to be from different mines in different parts of the world. One's a copper, one's a gold. Almost identical grain sizes by coincidence, but the water retention curves for the 2 are very different, and that comes from different mineralogies and different grain shapes. And different, the mineralogy is particularly relevant to the fine fraction as well. Can jump ahead of that. Okay, so let's now imagine this material deposited in a tailings dam or impoundment. You can have a phreatic surface. Below that, everywhere your water pressure increases linearly with depth, hydrostatic. But immediately above the phreatic surface, through capillary action, the water is sucked up into the pores and is held in a more or less saturated state, but in tension. So you can have a negative hydrostatic water pressure, and the extent of that capillary rise section depends on your air entry value divided by the unit weight of water. If it's caused by a drying process, that is, if your phreatic is gradually lowering, you're gradually drying out the tailings. It's the air entry suction that controls the height of the capillary rise. Conversely, if you're wetting the soil, for example, a rise of the phreatic surface or some rainfall event or something, the wetting means that the air expulsion value is critical in the height of the phreatic surface. Immediately above that, it deviates from linearity, and you have a chi-S profile that is also in a tensile phenomenon, but it has a very different, or it departs significantly from the hydrostatic condition. Okay, I'll quickly divert and talk about strength and stability problems generally. This is relevant to all types of civil. We solved the unsaturated case using a slipline theory. So we can look at things like bearing capacity of footings, stability of slopes, earth pressures on retaining walls. By putting linear relationships for chi-S with depth into the governing equations. So if our chi-S profile can be approximated as a straight line with depth. So it has a value of chi-s 0 at the ground surface and then might reduce with depth. If you can approximate it using a straight line, we can go forward and do some really nice things. Pardon me. Likewise, our cohesion can vary with depth as well. And we found when solving these problems, the dimensionless groups which govern stability have a repeating appearance of suction inside them. The governing dimensionless groups here show that there's a type of cohesion in the non-dimensionalization that depends on the value at the ground surface plus the chi-s at the ground surface multiplied by tan phi, and then there's a surcharge part. But there's also a unit weight part to the dimensionalization. You've got your gamma plus the rate of change of your cohesion plus the rate of change of your chi-s with depth. And they all sort of act together in the same way as well. And this gives rise to what can be called an equivalent method. You can put suction and its variation with depth into your stability calculations using these simple equivalent expressions. Your equivalent cohesion is the value at the ground surface plus the value of chi-s at the ground surface times the tangent of the friction angle. And then your equivalent unit weight also needs to be defined as your total unit weight plus the rate of change of your cohesion and chi-s incorporated as well. And that means that when using a software like a Slope W or one of these other commercial packages, you don't need to deal with the unsaturated soil features at all. You can model it as a total stress problem and put suction influences into your cohesion and unit weight, and you'll get the correct answer from a strength and stability point of view. This will ensure that the dimensionless groups which govern the problem do not change and represent those which are most relevant. Now, the chi-s profile that you put in must be representative of a worst case, so perhaps something to do with a wetting event involving the wetting curve in some way. And it's very powerful. The assumption here is also that the chi-s profile doesn't change much during the deformation leading up to failure. And that is reasonably accurate when you have large air volumes in your soil or small degrees of saturation. And we've done a whole lot of research confirming that. So I get my students to do this, for example, using Slope W. I give them an unsaturated soil slope. I say, well, these are the dimensionless groups that define the problem, the unit weights and cohesions. These are the real numbers here. There's a surcharge of 228. And this is the chi-s profile. So they can use this equivalent method to define alternate unit weights and cohesions, set the pore pressure parts to 0. Essentially, it's a total stress analysis inside the software. The dimensionless groups are identical, and you can then run the analysis. I also get them to put in outrageous numbers, like a unit weight of 78. All right, there's no soil on Earth that has anything like that. And then some ridiculous cohesion and surcharge that is a real departure from the exact numbers. But that doesn't matter. When you combine these parameters together, you get the same dimensionless groups as the original problem. So the mechanics are preserved. And when they run the stability analysis using all the different combinations of parameters, they get the same factor of safety. So it just highlights that the dimensionless groups control the stability, not the individual parameters used to make them up. So this just is a nice learning exercise for the students. Okay, let's get on to CPT. So I'm going to quickly give some background on what's been done in the past, highlight the importance of the drainage conditions, and then talk about applications and examples in tailings, and also finish up with some of the latest work we're doing on liquefaction, post-liquefaction strengths for unsaturated materials. So some of the earliest CPT work in very primitive, essentially a compaction mold They're just pushing small cones in. They're showing for a clean sand that when your degree of saturation is less than 10%, your cone resistance rises a lot through that capillary action. More sophisticated work a bit later on, using larger cones at the end, at a site at the end of wet and dry seasons. You can see at the end of a dry season, when there's a large suction, your cone resistance is roughly double that at the end of a wet season. These are some more results in a clean sand. On the left here, you can see that as suction increases to maybe 200 kilopascals, your QC is around 4 megapascals, whereas for the saturated case, it's only around 2 megapascals. You see the cone resistance is roughly doubled due to the presence of suction. We've done other tests on well-graded soils like a tailings. But anyway, there's a lot of evidence that suction does a lot to your QC. But what is happening from a drainage point of view inside the soil or the tailings? Certainly from a practical point of view, we would like to assume that suction is constant or Chi-S is constant. That would really simplify the interpretations. It means that the Chi-S which prevails around the penetrating cone is identical to what was initially present inside the tailings, okay? That would be a great thing to assume if we could. But realistically, when you push a cone quickly, Chi-S might change, but we do know for sure the water content is constant. There's not enough time for water to drain in or out in most cases, right? So that is a constant water content drainage condition, if you like. But sometimes the air can't drain out either. If the air is in isolated bubbles inside the tailings, as you push a cone, the air mass has to change. It has to be a constant as well. We call it a constant mass condition. You have to remember that air is very compressible, so we can't say that the air volume is constant. In fact, it's certainly not, but its mass is a constant. So we can explore all these different drainage conditions experimentally as well as theoretically using cavity expansion theory. And that we've spent many years doing that. And these are the main discoveries. We know partial saturation permits volume change because air is compressible. And that can cause a cone result in an unsaturated clay to look like you're pushing through a dense, drained, saturated sand because you've got a stiff response, but you've also got volume change. Even though you're pushing in a clay, you're getting volume change. The cone result will look like you're pushing in a sand. The soil behaviour type number will come out as a sand, even though you're pushing in a clay. But when the volume of air relative to the overall volume is larger than about 0.15, we know that a constant suction or a constant Chi-S give virtually identical responses.
Could you please shortly explain what the cavity expansion is for? Okay, the cavity expansion theory is an analogue to a penetrating cone. If you have a dot in a soil that grows and turns into a sphere and turns into a bigger and bigger sphere, we can model that theoretically, and we can track the pressures on the cavity wall causing the expansion. And the idea is that the pressures causing the expansion are roughly similar to the QCs pushing on the tip of a cone, right? A cone has to create a cavity when you push it into the ground, and the cone tip, although it's a cone, is roughly similar to a sphere. So there is a parallel between what we observe using cavity expansion theory and cone testing, right? It's a very common analogue that we use. You can also model an expanding sphere, an expanding cylinder. There's a two-dimensional version, but this expanding cylinder is not quite as close to the cone problem as an expanding sphere. Okay. Yeah.
So the discoveries were that constant chi-s, constant suction, give more or less the same results from a cavity expansion analysis as a constant moisture content condition when your degree of saturation is low. And that's because there's enough air in the system so that the soil deformation which occurs is quite large and roughly resembles that of a drained penetration where you have a constant pore pressure. Okay, and that's why we see those two similarities there. But when the volume of air is less than about 15% of the overall volume, things suddenly change. And there is a step change as well. It's not gradual. Suddenly the air volume is sufficiently small so that it remains trapped inside the soil or the tailings. It's not at all continuous and vented to the atmosphere. And instead, as you push a cone, the air stays trapped and the pressure builds up and obeys Boyle's law, and you get a little bit of volume change, but not as much as you would for a saturated drained condition. And we need to model that using constant mass, which is reasonably easy to do, but it just creates some complexity when we try and develop practical guidelines for that low volume of air condition. I'll jump through that, but I'm running out of time here. This is a nice example of how suction and the presence of air causes a significant change in the behaviour. This is CPT data for a quartz marine sand with around 8% fines. This is used to construct the airport at Hong Kong, I believe. When you have saturated conditions and you push a cone and you do everything properly, and you plot your normalized cone resistance against a friction angle, this is where all the data plots. You know, it's borderline dilative, contractive. It's a silt sand mixture according to the soil behavior type. Now, if the water table is lowered, same material, same state, same density, but now there's air present in that material. When you push the cone and ignore suction, so you compute these normalized cone resistances by using a total stress instead of effective stress in that denominator, the data plots up here. It looks like you are now pushing through a dense sand, even though you're pushing through a borderline soft, medium dense silt sand mixture. Okay, so that partial saturation influence is causing an apparent behavior change to, or a real behavior change to the soil. But if you're not careful, you will incorrectly classify that as a dense sand when it's not. Okay. Okay, now onto the tailings. So again, thank you very much to the sponsors and all the contributors here. This is more or less 5 years of research from a whole lot of people at the University of New South Wales and the University of Western Australia in particular. So the two tailings, gold and copper, a lot of the work I'll show is in this paper in geotechnique, which is available online, open access. So go and check it out if you want more information. I've shown these already. These are the critical state lines that depend on suction for the two tailings, water retention curves, and but here are the cone results. Now, using two calibration chambers, one large, one small, two, or in fact, 3 different cone sizes and a whole lot of different penetration rates, we were able to discover a few things. In particular, we found uniqueness between a saturated drained cone penetration and an unsaturated penetration. So the saturated results are the solid symbols, the unsaturated results are the hollow. And you can see they obey the same trends in this normalized plot. And that is because drained conditions prevail in both cases. The saturated tests were performed very, very slowly, so we knew drainage was complete. The unsaturated tests we performed quickly, but there was enough air present inside the tailings so that the volume change which occurred made the tailings look as though it was drained or pseudo-drained. And that's how we observe this uniqueness. The state parameter for saturated cases is very simple to determine using the critical state line, but we had to account for the shifted critical state line for the unsaturated cases as well in defining that state parameter to see this uniqueness. The same observed was true for the other tailings, uniqueness more or less for the saturated and unsaturated cases when we have large volumes of air present, larger than around 15% of the overall volume. It was only for lesser volumes of air, here this is 9%, here 7%, here's nearly 2%, that we see a departure from that pseudo-drained response. Okay, and this is significant. This is where we have to apply a slightly different interpretation technique to the results. But when we have large air volumes, we see uniqueness with the saturated tests. What are the conditions required for uniqueness? Like I said, large air volumes, and we think 15% is that critical number where it suddenly becomes pseudo-drained. And we have to account for the shifted critical state line in the unsaturated state parameters. When it less than 15% of air volume, we need to look at some partially drained, partially saturated phenomenon, and I'll get onto that in a second. But also these two tailings being very silty, we had to do the cone testing very, very slowly to ensure full drainage occurred. If we did standard penetration rates, we would have partial drainage or possibly an undrained condition where we would see a departure and some non-uniqueness. An alternate presentation of the results is shown here, and this has intentionally taken out knowledge of the shifted critical state lines. So there's no reference to state parameter inside these, okay? But you can plot a normalised cone resistance using a total mean stress against a void ratio, and at different mean stresses and different gravimetric water contents, we see these straight lines, these families of straight lines form, and you get slightly different plots for the two tailings types. But I've shown this because this is something that a mine could determine for their particular site using, you know, their extensive data records of cone testing over many decades, perhaps, where they've got knowledge of void ratio, water content, cone resistance, plot on these types of charts and can construct a family of lines that help you interpret your data in the future. I must also note that in constructing these charts, I assumed the hydraulic state of the tailings when unsaturated lies exactly halfway between your main wetting curve and your main drying curve. So it's not a drying event or a wetting event, it's something in between. And we think generally most unsaturated soils and tailings lie somewhere in between the main drying and wetting curve. Okay, there's field data that shows this. This is for some field monitoring of the soil slope over 2 years. The real hydraulic states that we measured were always located somewhere on this, or close to this red dashed line through here, whereas the main drying curve out here and main wetting curve out here, which we determined experimentally, were never really encountered in the field. So normal seasonal changes of wetting and drying, which are cyclic and change from 1 month to the next, mean that your state is always hovering somewhere between your wetting and drying curve, usually. So that's a reasonable assumption, practically speaking, most of the time. Okay, let's look at some laboratory correlations and how we can use those to interpret field data. Now, this is where we've got some cone testing in a saturated section of tailings, but we've used two different cone velocities inside the tailings. One is the normal 2 centimetres per second, where undrained conditions prevail, and the other cone result slowed down the penetration rate to 0.4 centimetres per second for a 1 metre section, knowing that drained conditions would prevail. So if we look here, the CPT, the light grey one here is when the cone resistance was slowed down. So we have drained conditions, and the black one everywhere is undrained, where we have the faster penetration rate. We can use those laboratory correlations, which are for drained conditions, to now determine the state parameter for this 1 metre section of the drained CPT. And then knowing the state parameter, we can then relate it to the fast cone penetrations, which occur under undrained conditions, to determine a new relationship that applies for undrained conditions. And that's what has been done over here on the right. This is the unique line that we determined experimentally for drained conditions, this black continuous line. But this newly established line for undrained conditions could be determined using that combination of two different cone results. Notice that the relationship between your normalized cone resistance and state parameter is very different for drained and undrained conditions. Okay, so you need to be very mindful of your drainage in your particular tailings dam when you're playing around with these types of presentations. Is it for drained? Is it for undrained? Or is it something in between, partially drained? The charts inside the Jeffreys and Bean textbook, which let you recover a K bar and an M bar using lambda 10 and so on, generally are charts showing data for when drained conditions prevail. Okay, so applying those to an undrained state when you have an undrained condition around your cone is probably not something I would do or recommend. Okay, you get very different K bar and M bar for undrained conditions, and I don't believe one relationship with lambda 10 will capture both drained and undrained conditions. This is now a case where we have a cone penetration in an unsaturated section of a tailings dam. Or in fact, I think if we look carefully at the pore pressures which build up around the cone, they're essentially doing nothing inside the unsaturated section. The piezometers at the cone tip generally are unable to measure negative water pressures unless they're being saturated using a very thorough specialised technique. Generally, they'll just register 0. And if you're lucky, it won't desaturate either. It'll stay saturated. And then when you hit a saturated layer, you start to see these spikes in your pore pressures and you measure the usual sort of things. So I'm using this data, I'm saying that these near zero pore pressures represent unsaturated sections, and the bits where you get spikes are saturated. And these are the corresponding QC results. So we can use those, that experimentally determined relationship to now recover the state parameter and a void ratio for that unsaturated section. And that's what's shown here. And I've compared the void ratios to those values recovered from block samples at nearby the CPTs, and you get good agreements. I just want to go back to this figure because there is a section just above the phreatic surface where this particular cone was measuring negative water pressures reasonably well. And then it got to a certain point where the pore pressures became 0. So I'm guessing in this region here, it's possible you've got a saturated section with some capillary rise where negative water pressures are present, and the cone is reasonably well measuring those negative pressures. And then suddenly, when it desaturates above that capillary rise, you have this zero pressure response. So you can make some reasonable estimates of extensive capillary rise sections and so on when you've got data that looks like that. Jump through that. I'll get on to strength and instability now. When you have, well, here degrees of saturation of 63% or larger, very loose void ratios. In a closed system, rapid loading condition, you get a response that looks a bit like a saturated, undrained case where you get some kind of increase and then a peak, some kind of instability condition, and then the strength reduces to some post-liquefaction strength, let's say, at larger deformations. And all the time you're getting volume change or a reduction in your void ratio inside the experiments. It's no longer a constant volume condition. So we did a whole lot of triaxles like this and tried to identify some trends between this post-liquefaction strength and initial state parameter. We also found that the instability line, that's the peak of those stress strain curves, depends very much on your degree of saturation. And in fact, it becomes steeper as your degree of saturation reduces. But here's a plot of these post-liquefaction strengths normalized by a mean stress against a state parameter. These are the dots that we've accumulated from the triaxles. The numbers next to them are the initial degrees of saturation. These continuous grey lines over here are saturated relationships between strength and state parameter. And now we can put on top of those some results for unsaturated cases as well. Now, I've been a bit tricky here. I've called this a modified state parameter. So it's a state parameter determined using the saturated critical state line, because that's something a practitioner can do. And the mean stress used in the normalizing quantity on the vertical axis is a total. Again, you don't need knowledge of IS to determine that. But you can see that this post-liquefaction strength ratio is now maybe 0.15 for a degree of saturation of 75%. So a little bit more than what it would be if it was saturated. So you're getting some benefits from the partial saturation here. This is a plot that just summarizes what I think is state of the practice. So for conditions below your phreatic, saturated soil mechanics applies. Capillary rise section above, again, saturated soil mechanics applies, but you must put your negative water pressure into your effective stress when you interpret your cones, when you assign an undrained strength ratio. Your effective stress must have that negative water pressure built into it. All the usual things apply: Skempton's A bar, A, B bar, and undrained shear strength and relationships with your state parameter and so on. At very dry sections, when you've got more than 15% of air present, tailings will behave as a pseudo-drained material. The Chi-S is essentially constant. And you can apply sort of drained concepts of soil mechanics to your CPT interpretations and stability assessments. Define your equivalent cohesion, as I've talked about earlier, and so on. And go forward with a design. The idea of an undrained strength doesn't have much relevance in that section. You've got a lot of volume change during deformation. Nothing like a constant volume condition. So don't try and use terms like undrained shear strength. They just don't have any relevance. Now, this intermediate section between your capillary rise and that drier material above is where we've still got a few knowledge gaps that we're dealing with now. You've got this partially drained, partially saturated scenario. And my advice to tailings engineers here is to do triaxial tests in a closed system condition. So close the valves. You can test very quickly, make no effort to measure pore pressures. You don't need them, but just interpret your test results using the total stresses that you apply. You recover a phi total and a cohesion or a C total that you can then use in your stability calculations. make sure that the initial states of your samples are similar to what you expect in the tailings, and that the load paths you apply are similar to what you expect in the tailings, because these I and C terms depends very much on those two things. Don't use concepts of undrained shear strength ratios, etc. They have no meaning in these unsaturated sections. Okay, this is some of our recent work. This is focusing just on very low volumes of air. So you've got this partial saturation, partial drainage type phenomenon, closed system conditions prevail. And we've plotted using cavity expansion theory and support of experimental measurements how your normalized cone resistance varies with state parameter. You've got a saturated undrained condition down here with a dashed dot line, saturated drain condition up here with a continuous line. And then as your volume of air transitions from around 15% for this drained case down to 0 for the undrained, you get this shifting trend between your cone and state parameter. Partial saturation has a lot of similarities to partial drainage in a saturated case. And that's because with partial saturation, you get a little bit of volume change, but not as much as you do if it was fully drained. And same with partial drainage. You get a little bit of volume change, but not as much as you do if it was fully drained. And I've shown this using some cavity expansion work, how you can have, for example, a very low velocity of your cone. You get drain conditions, a very large velocity, undrained, and it will transition from one to the other with partial drainage, much in the same way as it does with progressively adding more and more air to an unsaturated material. So this is what we're working on now, to come up with some simple tricks to establish a K bar and an M bar that you can then use in your screening level assessments of a tailings dam. If you know your non-dimensional velocity, for example, or your volume of air relative to the total volume, these are the types of responses you'll see for saturated drains, or when you've got very small volumes of air, you've got your K bar and M bar being equal to this is large volumes of air, I should say. You've got your K bar and M bar being equal to your drained values, which you can recover from the Jeffreys and Bean charts. But as your non-dimensional velocity increases or the volume of air reduces, the K bar and M bar change very much and eventually approach the saturated undrained values over here at large values. So just need to populate this chart with some real data. This is essentially a theoretical prediction at the moment, but this is what we're working on right now and what the future of CPT interpretation may look like.
From the work of
Arturo's work we've tested about 5 tailings now. I just need to put it all together. Still in the middle of it, let's say. Yeah. Another couple of things to be wary of is the use of the widget, which is becoming fairly common now in practice. It has built into it a correction factor which converts a normalized cone cavity expansion result to a normalized cone resistance. The factor is around 2 inside that widget, but my experience is that correction factor is a bit too small. I'm seeing numbers closer to 4 or 6. So your widget can underpredict what your cone resistance might be. So just be really careful of that. This is where I've plotted normalized cone resistance against cavity wall pressures using real data, and the ratio is 6.3 in this case. Another thing to be wary of is that the widget outputs contain errors as large as 10%. I'm not exactly sure why that is. It might be something to do with the numerical tolerances inside it, or the fact that it's expanding a cavity that doesn't start from zero. I'm not familiar, but it could be something like that that causes these errors. Anyway, so look, this is getting into summary and conclusions now. As people apply unsaturated soil mechanics, they're doing some really good things. They're determining the water retention curves, usually by engaging universities. Really smart, you need that all the time. And people are using this equivalent cohesion. It's been around for a while. It's not a new concept, but there's also equivalent unit weight that perhaps people are less familiar with that should also be used if you've got a steep gradient of your suction. People are also making a lot of mistakes. They're mistaking total suction with matrix suction. And this is an area that needs a lot more research, but total suction is osmotic plus matrix, but the osmotic part acts very differently. It acts on the clay minerals and changes, diffuse double layers and things, and that does not always cause a mechanical change to the material in the same way a matrix suction does. So just be really careful not getting off track there. Not understanding hydraulic hysteresis is a big one. Soils and tailings have a distinct drying curve and wetting curve. But often a practitioner say, lab, please generate the drying curve. Great, got it. Now I'm going to apply it to a wetting event. Wrong. You need the wetting curve for a wetting event, okay? Or something in between if you're hovering between drying and wetting processes. So get that part sorted out as well. Not realising suction needs a multiplier of chi or something before it's added into the effective stress is another oversight. Thinking that a suction of 1,000 kilopascals in a rock fill is a big deal. It's not, because the chi is so small, almost zero. The suction does virtually nothing to the strength in that particular material, okay? These devices which you see around, MPS 6s, Terroses, to measure suction seem to be really good, and they are most of the time, as long as your material is undergoing a drying path. The calibration curves built into those devices is only for drying events. So if your material is wetting for some reason, throw the data away. You can't use it, okay? Using language like undrained shear strength for an unsaturated material is not smart. That is a strength that only works for constant volume conditions, which you'd never have for an unsaturated case. Inserting piezometers in an unsaturated material, be really careful. The suction can cause them to desaturate, especially if it's larger than about 100 kilopascals. So those devices can become unreliable, especially if they're used to trigger alarms and so on. So be really careful. Only bury them in and so they stay saturated. And ignoring capillary rise, I think it's not something we should do. We should try and put it in if we can. And some of the things just to be looking out for as a practitioner. Key messages: equivalent, cohesion, unit weights. Proceed with designs using total stress. Great to do in software. What else is the key message here? The volume of air relative to the total volume is key. If it's larger than 15%, drain conditions prevail. If it's less than it's a bit tricky when we use this kind of total stress strength parameters. Now, there's a whole lot of references listed there. A lot of them are free access, and consistent in the mechanics and terminologies used. So jump onto those if you want to have a look. There's an interesting one here by Arturo Jimenez and myself, where for fractal materials, relate the water retention curve to simple parameters extracted from the particle size distribution. And that can avoid time-consuming lab testing. And because I'm in Santiago, and Santiago is gravel, I've used that Jimenez and Russell procedure to estimate the water retention curve for Santiago gravel. So here we go. I've assumed 3% clay and a void ratio 0.254. I have no idea how accurate these are, but from one paper I saw, it had a dry density of 21 unit weight, and that gives that void ratio. So then for a moisture content of 5% and a friction angle of 45 degrees, I get a chi-S of 21 kilopascals and an equivalent cohesion of also 21 kilopascals. Now, this is due to capillary effects. This is added on to the saturated cohesion, if there is such a thing. Now, you told me something about 20 kilopascals with the gravel earlier. Was it a saturated cohesion or a moist cohesion? When it was saturated, though. Okay, so you would have to add that 20 on top of this. So the equivalent cohesion would be around 40. So you can, I don't know if that's observed. It might give some explanations to why cuts can stand unsupported for several meters before they collapse. Yeah. So just a little disclaimer, though, the procedure was developed for soils and tailings nowhere near as coarse as the gravel. So we're possibly pushing beyond the limits of its applicability. But anyway, just a little, there you go. All right, I'll stop there. Got a little bit out of time, but I think we've got time for a few questions.
Thank you very much, Adrian. I wonder if there are questions from from online, from the colleagues in the Zoom room. Any questions?
Thank you for the presentation. Very good. I'm thinking about the CPT interpretation. Can you or would you recommend to interpret it a state of saturation with the BQ parameter, the normalized water pressure parameter?
Yeah, so it's a good question. So the BQ is, like I say, traditionally used for a saturated, undrained or partially drained response. I haven't tried to define an alternate B something for an unsaturated state. The reason is that you can't really measure pore pressures reliably in an unsaturated. So, you're just getting zeros and you can't really come up with a B of any kind. Does that answer your question? Yeah, okay.
Any questions? Questions? I did some questions. I would like to do some more questions. Happens when it comes to testing. What are the key procedures in testing triaxial specimens under unsaturated? What are the key aspects that make a test a good test? How do you guarantee that you are, for instance, you are having a uniform distribution of the saturation, of the partial saturation?
Yeah, that's a good question. So in a perfect world, you would form your sample maybe by moist tamping, or so it starts unsaturated, and then you put it in your machine, and then you flood it with water, so it's more or less saturated, and then you then you drain it out to make it unsaturated in a controlled way, and it's moving along a drying curve. You know that, okay? And the other extreme is start with a very, very dry material and then put it in your machine and gradually wet it and maybe stop before it gets fully saturated and test it there as well. But it's very slow because you have to wait for moisture equilibrium as well. So you need to let it sit for maybe a week before you even start shearing it.
Oh, that's an interesting point. How much time? It's a triaxial in specimen 5 per 10 centimeters.
Yeah.
A small specimen. How much time? It's way longer than a regular 6 hours triaxial satellite.
Yeah. So it can take several weeks depending on if it's got high clay contents. It can take several weeks to get it to your target suction.
Well, I'm thinking of a tailings.
Yeah.
Of a tailings.
Silty tailings.
Under control.
Yeah. Silty, even a silty tailings can take a week. Yeah. One of them we've got now has got fairly high clay content and it's taking several weeks. Yeah. Now, but you can also, and what I would recommend industry do is not worry about this and just get the sample to the right moisture content and void ratio through moist tamping or whatever process they like, put it in their machine and just, and then essentially test it straight away. But close the valves, keeping it a closed system. And if the volume of air is very low, and then they'll get CT, C total, phi total. And they should do lots of these tests, maybe, 8 or 10 or something, and they'll see their data and there'll be some scatter through it. And because the hydraulic states, the samples will be a little bit different. Some will be a little bit closer to a wetting curve, some will be closer to a drying curve. But, practically speaking, you can look at the scatter and then decide, well, maybe the lower bound is closer to the wetting curve, and that's what they use in their design, okay? And that's better than ignoring suction altogether or putting in some nonsensical undrained shear strength concept, which is what's currently done, right? So it's certainly an improvement, but not perfect, and can be done quickly. Now, if you've got large volumes of air in the tailings, again, do the same thing, but this time open the valves so it's essentially a drained test. Test it quickly again, and you'll see more or less a nice relationship between your strength and total stress, and you can recover your C equivalent and your phi from those results. And again, a bit of scatter and error on the lower bounds and things like that. But and just to be sure, in that case, where the valves are open, test some quickly, like in maybe 1 hour, bring it to the critical state, and test some slowly, like in 24 hours or 48 hours, bring it to the critical state. And theoretically, you should get almost the same strength relationship for those two scenarios, meaning that you've got partial drainage irrespective of the loading rate, and that gives you confidence that they're the right parameters to use. Yeah.
In terms of safety or a factor of safety, how, in general, under your experience, what are the differences that you see in the factor of safety?
They're huge. They're huge. There's one tailings dam I know of. The phreatic surface is quite low. It's roughly halfway down the tailings, and the critical slip surface is above it, right? But they've assigned an undrained strength ratio of, say, 0.1. Okay, and which is nonsensical. It's a saturated soil concept. The slip surface is entirely in an unsaturated material, and they've correctly set pore pressures to be 0. Well, that's not correct, but they've acknowledged that there's no hydrostatic water pressure, at least. But the real strength parameters should be a C equivalent of 5 kilopascals and a phi of 25 degrees or something. And it's going to give you a massively different factor of safety, maybe 2 or 3 times larger. Yeah. So it's significant. Yes.
It's like everything is super.
I don't know if there's two,
Maybe from the
there's three chats on there. I don't know if they're questions. How do we see those? How do we go to Zoom? Here we go. How do I? Oh, here we go. And someone wants to see the references again.
yeah, the reference. They're asking for that.
So if you email me directly, I can send you the list or the presentation, and can't read those others. I think they're just saying,
Yeah,
take off the mute and thank you. Okay. Right.
we are done.
We're done.
Yeah. Thank you very much, Adrian. Great presentation.
Thank you.
It's a whole new world. A whole new world.
Yeah.
Saturated soil mechanics. And a lot of fun. A lot of fun. Okay, I'll switch to Spanish.
Okay.
Muchas gracias a todos los que vinieron. Muchas gracias también a la audiencia, a los colegas que vinieron online. Muchas gracias por su presencia. Muchas gracias también a los colegas que vinieron el día de hoy. Así que eso. Thank you very much, Adrian. Seguimos en contacto. Vamos a seguir teniendo seminarios entretenidos de geotecnia, así que todo siempre muy bienvenido. Muchas gracias y nos vemos prontamente. Muchas gracias. Hey, these are good. Okay. We are good. Tratamos de ya no está grabando, sí.